All generative modeling shares a single objective: mapping a starting distribution of pure noise into a distribution of structured, meaningful data. The architectures that dominate this field today, diffusion and flow matching, reach that goal by solving complex differential equations. In practice, these models require an iterative loop during inference. To generate a single image, a sample passes through the network dozens of times, undergoing repeated solver steps. This multi-step requirement limits deployment speed and generates significant computational cost every time the network is run. To reach a one-step generation speed, researchers currently rely on complex workarounds like knowledge distillation or adversarial training. Scaling generative AI is restricted by this mathematical toll. High-quality generation currently demands an iterative calculation at the moment of creation. A new framework from researchers at MIT and Harvard suggests an alternative approach. They call these drifting models. Their thesis moves the entire burden of iterative evolution out of the inference phase and places it into the training phase. This creates a network acting as a single-pass function. It maps noise directly to data in one step without the need for an internal loop. Here, the network's output distribution evolves through standard optimization like stochastic gradient descent. As the model trains, the orange-generated distribution drifts to match the blue target data. This physical alignment is mirrored below. As the shapes converge, the training loss drops exponentially. This one-step method achieves a state-of-the-art 1.54 FID on ImageNet 256 without needing distillation from a larger model. Drifting models demonstrate that the training loop itself can serve as the solver, potentially removing the need for iterative math during inference. To build a one-step model, we need a function that accurately maps a noise distribution to the data distribution. The researchers achieve this using a localized drifting vector field, denoted as V. Here, the black dot represents a single generated sample, X. Two forces act on this sample. First, an attraction pulls it toward a batch of true positive data, shown in blue. Simultaneously, a repulsion force pushes the sample away from other generated negative data, shown in orange. The sum of these two vectors determines the final drift. This determines the exact magnitude and direction the sample must take to reach alignment. By calculating this vector for every sample in a batch, the model creates a map of how the entire distribution must physically shift. If the data is constantly drifting, how does the system know when to reach an equilibrium and stop? The system is governed by a constraint called antisymmetry. This means that swapping the generated and true distributions must result in a vector field that is the exact inverse of the original. Under this constraint, if the generated distribution perfectly matches the true distribution, the drift vector becomes 0. The samples stop moving because the target has been reached. Breaking this rule causes the training to fail. If attraction is weighted even slightly higher than repulsion, the generation quality degrades rapidly. Antisymmetry provides a mathematical guarantee that the model will only stabilize once it has achieved distributional alignment. Optimizing this is difficult because the vector field depends on a distribution that is constantly changing as the network updates. The researchers solve this using a stop gradient fixed point iteration. In the loss function, the model calculates the perfect drifted position for a sample and then freezes that target in place. The network then makes its current prediction, and standard mean-squared error pulls the weights toward that frozen target. Standard stochastic gradient descent then repeats this process over thousands of iterations. This bypasses the need for complex calculus during the generation itself. The network learns to map noise to data by chasing a series of perfectly calculated frozen targets throughout training. We can observe the result of this math as the vector field drags the probability mass into structured shapes. When given a checkerboard target, the orange unstructured blob physically stretches and separates into distinct tiles over the course of training. The loss curve tracks this progress precisely. We see significant drops in the graph exactly as the checkerboard corners snap into place. The field can also map continuous structures, like a spiral. By iteration 500, the mass has twisted into the basic shape of the target. At iteration 2000, the loss flattens. The drift has reached 0, locking the generated spiral into an exact match with the ground truth. The field exerts a calculable force on the data until the alignment is complete. Generating a photorealistic 256 by 256 image is significantly more complex than these 2D toy examples. If we calculate vector distances using raw pixels, the math fails. Pixel-level differences do not correspond well to how humans understand an image. To fix this, the researchers run the drifting loss calculation inside a dense feature space rather than on the raw pixels. They use a pre-trained latent masked autoencoder to extract semantic features. This ensures that the vectors attract and repulse concepts, like shapes and textures, rather than just raw colors. This decoupling is what allows the drifting paradigm to scale to high-fidelity imagery. The empirical results confirm the success of this approach. The drifting model achieves a state-of-the-art 1.54 FID. This model requires only one step to generate an image, compared to the 250 steps typically used by diffusion models like DIT. These results were achieved entirely from scratch, without distilling knowledge from an existing multi-step model. The researchers also demonstrated a 1.61 FID score when generating directly in pixel space, proving the drifting math remains robust even without latent structures. These uncurated samples show that theoretical efficiency translates directly into high visual fidelity. This research suggests that explicitly modeling diffusion trajectories at inference time may no longer be a requirement for high-quality generation. By utilizing the optimization process itself as a distribution solver, drifting models eliminate inference latency and provide a new direction for the architecture of generative AI.